Hey everybody, welcome to the Iphreaks show. Today on our panel we have Abbey Jackson.
Hello.
And Abbey, we've had you on as a guest before, but this is your first time as a panelist.
That is right. Yes. Sorry. I could.
Yourself.
Yeah. So I'm in Vancouver, BC, Canada, and I'm an iOS developer currently working on SDKs. But the funnest project I worked on before was I worked on the Intel Avant AR glasses that was shut down last year. And I mostly work in Swift. I've been on Swift since version 2, but recently I've been in Objective-C, and that's actually what our topic was about learning Objective-C as a Swift programmer.
Oh, definitely. Yeah, we loved having you on the show, so we thought it would be great to have you sit in as the panel. So welcome.
Glad to be back.
This episode is sponsored by Sentry.io. Recently, I came across a great tool for tracking and monitoring problems in my apps. Then I asked them if they wanted to sponsor the show and allow me to share my experience with you. Sentry provides a terrific interface for keeping track of what's going on with my app. It also tracks releases so I can tell if what I deployed makes things better or worse. They give full stack traces and as much information as possible about the situation when the error occurred to help you track down the errors. Plus, one thing I love, you can customize the context provided by Sentry. So, if you're looking for specific information about the request, you can provide it. It automatically scrubs passwords and secure information, and you can customize the scrubbing as well. Finally, it has a user feedback system built in that you can use to get information from your users. Oh, and I also love that they support open source to the point where they actually open sourced Sentry if you want to self-host it. Use the code devchat at Sentry.io to get 2 months free on Sentry's small plan. That's code devchat at Sentry.io.
And we have a guest today. Please welcome Michael Petrie.
Hello, how's it going?
Pretty good. Also known as Capsy around the internets. Capsy, can you tell us a little bit about yourself?
Yeah, so I currently live and work in Japan. I'm from New Zealand, and I work for a company called Zozo Technologies. So they make they're traditionally a fashion EC site. They're branching into more interesting sort of body measurement tech. So I'm quite heavily involved in that. I work a lot with Swift and Objective-C and C++, so it's sort of a mix of all of those. So it's a very interesting job. I get to speak a lot of Japanese, and there's a lot of interesting communication problems to be dealt with, which is a lot of fun. And as part of my personal projects, I'm very much into graphics and music and programming, so mixing those three as well. So I like something that can create some output.
Okay. Oh, very cool. So you came across our attention because of a talk you gave at TrySwift on ray tracing. Can you tell us a little bit about ray tracing and what that is?
Yeah, absolutely. So when I was, we all sort of submitted papers for the TrySwift talks. And traditionally with those kind of things, I always had the impression that, well, if you're going to submit something as part of your company and use company time to work on it, you've got to kind of talk about what your job is about. So it might be, if, for instance, if I do measurement framework stuff, it should be sort of, maybe how to use a C++ framework and Swift, something like that. So, while that stuff's kind of interesting, I was kind of like, if I'm going to submit something, I'd really love to do something that I want to do and I want to learn about. So I checked with everyone and they said, yeah, that's totally fine. You can do basically whatever you want. So I was like, okay, well, ray tracing is something I've always wanted to learn about. It seems sort of like quite an untouchable topic. Like it seemed quite difficult to me. So I really wanted to try and get into it and figure it out. And at the same time, using Swift so we could see how Swift could help us there, or what kind of advantages Swift could bring if we did some ray tracing in Swift. So I submitted my proposal and I got accepted, which is great. So I got to work on ray tracing for a wee while and learn about it from basically nothing. I didn't really know much about it. I had a little bit of sort of more traditional rasterizing graphics type experience, with like OpenGL and Metal. But ray tracing was a real sort of a real mystery to me. So it ended up being a lot of fun. I learned a whole load, and it was great to talk about it.
Very cool. Now, can you give us a brief description of what ray tracing is? Because I'm having trouble visualizing it. I've seen it.
Yeah, absolutely. So ray tracing is fundamentally, it's the same sort of technique used to render 3D graphics as what you would see in like a Pixar or a Disney film. It's fundamentally, it's very similar, and it works simply by taking every pixel on your screen and shooting rays from the point of view wherever you are in the 3D scene. And those rays, they go through the scene, and they go through all of the objects in the scene until they figure out when they hit something. So when they hit something, then you know, okay, based on the material properties of that object that you hit, you can change the color of that pixel. So say, for instance, if you shoot a ray into the middle of your scene and it hits, say, like a red cube, then you would look at those properties and you say, okay, I'm going to draw this color red. It gets interesting when you say, well, okay, I have a particular material that, say, might be reflective, or it might be like a mirror, say, for instance. So when you hit an object that has a material, reflective material like that, you wouldn't just color that pixel red. You'd create another ray at that intersection point, and you'll calculate the angle at which that ray bounces off and potentially hits other objects in the scene. So you can sort of understand how it starts to get very computationally intensive very quickly. If you have lots of sort of ray reflections and lots of rays to begin with, you can sort of get, millions of, I think some of the scenes I was working on maybe had a few million rays per image, but you can get up to billions of rays per image quite easily. So that's why it's traditionally being part of pre-rendered or offline rendering graphics for movies and that kind of thing. It's not quite yet ready for real time, although that is starting to change. NVIDIA have been pushing their RTX hardware very, very, very strongly recently, and that's has specific circuitry designed to deal with all of the ray collisions and all of the math involved with ray tracing there. So the future is very interesting for ray tracing. You might start seeing it in games and that kind of thing.
So, like, if you're trying to set up a real basic ray tracing, what do you call it, setup? Like, what would be a very basic one, like a hello world for ray tracing?
Okay, that's a very good question. So I think that the best way to get into ray tracing, the way I got into, was I read Pete Shirley's books. If you don't know Pete Shirley's books, he wrote some very sort of simple, they're actually called Ray Tracing in a Weekend, which is perfect, right? So the hello world for those is basically you set up a scene, 3D scene, and you set up a camera. Now in that scene, you just draw a sphere, like a perfectly round ball. And the reason for that is to calculate where the rays hit that sphere are very, very simple compared to, say, like a complex sort of animated mesh or something. So that's sort of your hello world. You'll see a lot of, if you search for ray tracing, you'll see lots and lots of images of spheres and lots of reflections and that kind of thing. But yeah, if you're looking to get into ray tracing, or if you're looking for a place to start, then Pete Shirley's books are great. They talk you through the whole thing. They don't get too heavy on the math. It goes into the math enough that you can get into it if you want, but it doesn't sort of, it's like some books, they'll have a whole chapter on the math, which is just like, if you're new to it, it just totally fries your brain before you're even writing any code.
Now, you said that the doing this is extremely computationally heavy, right? Because of the billions, potentially billions of rays bouncing all through the scenes. Do you think that this is something that we're going to be able to see come to handheld devices? Because I'm going to assume that right now it's pretty heavy for like a handheld game. And even when it comes to Mac versus Windows, a lot of the graphic systems out there or AR systems out there, you can't really even run them on Mac because they're not powerful enough. So what do you see for the future for that kind of stuff?
Yeah, absolutely. I mean, I think it's probably not ready for mobile. And the reason is that mobile is just, you've got your battery life and you've got you're running other apps at the same time. And then, I guess before we get into that discussion, you probably want to discuss the difference between real-time ray tracing and offline ray tracing. So the ray tracing I did was very much offline, in that you cannot, say for instance, if you have a predefined frame rate, like 60 frames or 30 frames per second, you have to draw an entire image within that time. If you can't do that, then it's going to be very slow. It's going to be very uncomfortable. So I think that the video I did for the TrySwift conference, it took maybe, I think it was in the range of 20 or 30 seconds per frame. So that's nowhere near real time. And that was on like a pretty powerful MacBook Pro. So you can imagine like moving that down to mobile, there are quite a few challenges there. But having said that, NVIDIA have been really pushing this RTX thing. So RTX is like a new sort of graphics sort of hardware technology that they're putting into a lot of their new graphics cards. And the idea is that you have circuitry that's specifically designed to run those calculations much faster than if you were to run them on, say, just a normal graphics card or on the CPU. And yeah, I mean, these are really big graphics cards that, like, they cost like $1,000 or something. But in the future, it's not hard to imagine that they might sort of get smaller and faster until they move into mobile, for instance.
So what did you demonstrate during your talk?
So during my talk, it should be on YouTube, if I can find it. Yeah, so there was during my talk, I only had 5 minutes. So it was a lightning talk, actually. So it was pretty short, pretty difficult to try and get so much information into such a short time. But basically, I built this very small, simple animation of some rotating spheres in Swift. It was about, I think, 500 lines of code. Didn't use any APIs. No, there's no metal. There's no sort of core graphics APIs or anything like that. It's literally just code, a whole bunch of math, and writing it out to a file. So I demonstrated that at the start of my talk, which I think was quite. I think it was quite interesting in the fact that perhaps a lot of people at the conference didn't realize that you could do that kind of thing with just code. I think a lot of people perhaps think that you might need like a complicated API or a lot of setup or a lot of code to do something like that. So I think if there was any sort of takeaway from that or anything I wanted to get across to people was that you can actually do quite interesting things without having to rely on lots of language features or lots of APIs or lots of frameworks or anything like that.
No, it's very cool. So I'm searching the internet, and looks like the talk is available online. It's on YouTube. It's called Graphics Like Pixar Using Swift. Is that the right one?
That sounds like the one. Yes, indeed.
Okay. Yeah, I look forward to seeing what it is. So what's involved with writing this in Swift? Like, how do we set this up?
Now, the code for this is actually on GitHub. So that's probably the easiest way to explain it. But it is very simple. It's yeah. So if there's a link that we can share with the listeners after that, that would probably be great. But just to give a brief overview, basically it's a recursive approach, ray tracing. So the ray tracing algorithm, as it were, would iterate through each pixel on the screen, and for each pixel, it would define, well, before we do that, we define a virtual camera in our scene. And from that camera point in our scene, we shoot rays through each pixel, and we figure out, for each of those rays, we figure out what objects in the scene we've hit. And then for each of those hits, we iterate through a bunch of materials until we find the material for that object. And based on the material, maybe you'll shoot out more rays, or maybe you return a color. So if you return a color, We literally just color that pixel in. So the pixel is just a big sort of memory buffer. And then we write out that buffer to an image. So it's really simple, actually. And for the animation, I think I wrote out maybe about 8 seconds at maybe 30 frames a second. So it was I think 240 frames. So there was a little animation mechanism which moved the camera slightly in a rotation every frame. So it would print out one of these frames, move the camera slightly, print out another one, do that 240 times. And at the end, you have 240 images sitting on your hard drive. There's another little script that used FFmpeg to convert those into a video. And there you go. You've got a very simple video. Obviously, that's a world away from what someone like Pixar would do. But I think it was important to sort of be able to demonstrate that you can actually create a movie without having to do a lot, and being able to demonstrate the path of that process, I think, was quite important.
Okay, what technologies are you using to create the material? Are you using metal, or how is this done?
So I'm just looking through the code here. That will probably help me. So for the I don't know. Can you see the animation itself? It might help if we can, if you know what I'm talking about. Is that possible to view it?
I'm not sure.
Sorry, I don't have a link here. Okay, maybe I'll have to get you to imagine it. But basically, the scene I drew was it was just a bunch of spheres. I think about 20 or 30 spheres, and they were sort of randomly laid out, different sizes, different colors. And each of those had sort of one of three basic materials. So you define your material types, but there are, when you get down to it, there's sort of only a few basic physical properties that each material has. So in the case of the animation I built, you have something called a Lambertian material. A Lambertian material is, if you imagine like a real world substance like, say, chalk, or something that just doesn't reflect anything. It's well, that's not entirely true. It does reflect, but it's not shiny at all. So another example would be something like some types of wood are very, very Lambertian. And then there was a metal material, which is pretty obvious. It's just a metal, and that also has a fuzz factor. So the fuzz factor in the metal is like how much the metal blurs the reflection, if you know what I mean. So if you imagine like your MacBook Pro, it would have a very high fuzz factor because it's metal, but it's still not really reflecting anything like a mirror. And then on the other end of the spectrum, you'd have a mirror, which is a very low fuzz factor. It's reflecting rays one-to-one. Like if you shoot a ray at a piece of metal with a very low fuzz factor, it will bounce off like a ball, if that makes sense.
This episode is sponsored by GitLab Commit. GitLab's inaugural user event brings together the GitLab community to connect, learn, and inspire. Speakers will showcase the power of DevOps in action through strategy and technology decisions, lessons learned, behind-the-scenes looks at the development lifecycle, and more. Learn how to innovate the future of software development by registering today. GitLab Commit Brooklyn, September 17th, and GitLab Commit London, October 9th. You can find it at devchat.tv/GitLab Commit.
Okay, so I'm looking at the video you have up here, and it looks like a chessboard, like checker pattern. You got some marbles on there, like a red.
Yeah, that's them.
And that's one where you're shooting a ray at the red marble. It doesn't reflect, so you get the color. And
that's correct.
Yeah, so I'm looking at another one which has more of a mirror thing. You shoot the ray at it, it bounces off, goes to the floor, goes to like the surface, so you can kind of see the checkerboard in the marble.
Yeah. So okay. Yeah, so that would be a metal reflector, or a metal material. Sorry.
Cool. How did you get the model for the marbles and the board and all this?
So all of that is just generated with code. There's no like meshes or 3D model information or anything like that. So And that was sort of what I touched on with the talk, is like the fundamental hello world thing is like how to create a sphere in ray tracing. And there's a mathematical equation to do it. I won't get into it too much, but it sort of involves solving two equations. So you have an equation for a ray, which is like you have an origin, and then you have a direction, and you have a distance along that direction. And that can define the array and where it might hit. And then for a sphere, well, if you think about a sphere, you can actually have 3 different points of contact, if that makes sense, or 3 different types of contact. So you can have no contact, which means you just completely miss the sphere. You can just share the surface of the sphere, which is pretty unlikely, but it does happen. And then you can go through it. So if you hit one side of the sphere, you could imagine the ray would keep on going and hit the other side. So the equation sort of is based on those 3 scenarios. And obviously, if you miss it, you don't draw anything. If you hit it in either of the other 2 cases, then you look at that material that it holds, and then you draw a pixel.
So what if you were working on something where you had something more than a sphere? What kinds of models could you use with this? Or how could you do something that was, you're doing a cat video?
A cat video. That's a very good question. That's sort of taking ray tracing from like hello world to like thousands and thousands of lines of code and lots and lots of stuff. But that's a very good question, because I did actually do something like that. And to be honest, for my TrySwift talk, I actually really wanted to do something like that. I like classic cars. So I had this model I found on the internet of a Mercedes 300 SL Roadster. It's kind of a classic Mercedes. And I wanted to draw that rotating around instead of just the spheres, because I thought that would be really cool. And it would, like spheres are kind of abstract, but when you take like a real world object, it sort of makes sense to a lot of people. So unfortunately, I really worked on that, but I didn't quite get it done in time for the TrySwift talk, which was probably good, because I think it would have been too much information anyway to pack into such a short talk. But I did actually post on my Twitter. If you go to my Twitter, there's a picture of a movie of a rotating Mercedes. It's very similar to the TrySwift thing, except it's a Mercedes-Benz rotating around. And it's got, like a shiny paint reflection material. And it uses something called normal mapping, which is like taking textures and applying surface properties to them, so they kind of look a little bit 3D. But to answer your question, the way to do that, it was very difficult. It was extremely difficult. It really, 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 really almost broke me, but it was well worth it. Unfortunately, I couldn't quite get that going in Swift though. I had to fall back to C++. C++ was just better for the job there. But there was a very good paper that I followed by a guy called Ingo Wald, and he's sort of quite well known. I think he's actually the CTO of NVIDIA for ray tracing now. But he wrote a PhD on how to do fast real-time ray tracing just on the CPU. And this was quite old. This is like 2004. He wrote this. It's his thesis, and it covered a lot of like how to make that fast and how to do it in the first place. So to answer your question in a roundabout way, if you have something like a cat or a car or whatever, you'll start off usually with a mesh. So a mesh will just be a whole bunch of points, and those points define triangles, if that makes sense. So when you take those triangles, you can then, you need what's called a triangle ray intersection algorithm. There are a whole bunch of different ones. Most famous is probably called the Molar Trombor, which involves a whole bunch of interesting math, and there's a lot of linear algebra used to work that out. But the idea is it basically becomes the same thing as the spheres once you have that triangle intersection. So you can go through, instead of just iterating through all the spheres in your scene, you then iterate through all of the triangles in your scene, and you figure out which rays add in which triangles, and you draw the material. The problem with that is that if you have a big mesh, And in the Mercedes-Benz render, if you look at it, I think it has close to 1 million triangles. So if you do the math on that, it gets pretty insane pretty quickly. If you take, it's worth pointing out as well, when you ray trace, you don't normally send one ray per pixel. So if you do, it sort of looks a bit naff. You need to normally send, quite a few rays per pixel to get an anti-aliasing effect. So if you imagine if you have even just a small image, say 200 by 300, and you send, say, 16 rays per pixel, and then multiply each of those rays by 1 million triangles in your scene, it just gets unbearably slow. It's horrible. I tried it first with the Mercedes render, and I think it took about 15 minutes, and this is just a naive implementation, 15 minutes, and that was actually a low detail model. So the original model was like 1 million triangles, but the low detail model was only 70,000, and that still took 15 minutes for one picture. So you can imagine multiplying that by 240, you'd be there for days just to get an animation out, and it didn't look that great anyway. So now this is a well-known problem, obviously, and that's what Ingo Wald's thesis covers a lot, is how to speed up that process. How do we build structures and data structures and algorithms so that we don't have to iterate every single triangle for every single ray? And the answer is, of course, you start building these, they're called spatial subdivisions, or binary spatial partition. It's also called a KD tree. So binary space partitioning. Sorry, I forgot the name here. Early in the morning here. Yeah, binary space partitioning. So the idea is that you will surround your triangles. So if you have a set of 1 million triangles, you surround them with a big box, and then you'll split that box iteratively again and again and again, making a tree. And each little compartment or sub-box in that box will only contain a few triangles. So you keep doing that until you only have a few triangles in each box. And then when you send a ray, you can quickly figure out which, if you imagine it's like a binary search tree, where you can imagine with each child box, you can eliminate half of the triangles in the whole mesh. So instead of becoming like an ON problem, it then becomes like an O log N problem or something. And that speeds it up a lot. That gives it a huge speed up. I think when I first implemented that, as I say, it went from 15 minutes down to about 5 seconds for rendering the Mercedes-Benz.
And so all that studying for interviews that we have to do that we complain about we'll never use, it sounds like you found a use for it.
Absolutely, yeah. O numbers are definitely one, and I think that's where that whole big O notation comes from, is that it sort of becomes useful. If you're iterating over, say, 100 or even 1,000 objects, it really doesn't matter what algorithm you use, because computers are really insanely fast. But when you get to that level where you're iterating over potentially billions of objects, or you're doing billions of iterations, then it really does matter. It does make a huge difference.
I just have a question, if we can back up just a tiny bit. I'm wondering, for our listeners, and also myself, who don't have very much 3D or graphics rendering experience at all. When you're talking about making or using a mesh, where would someone who's just starting to learn this kind of stuff either get a mesh, or what kind of tools would they use to create a mesh to practice with or play around with?
That's a good question. So there are a number of sites on the internet where you can get quite good meshes. I think, I can't even remember the name of the one I got mine from. I think it was, I can't remember names, but maybe we can come up with a list afterwards. But there are a number of sites where you can download meshes for quite a small, I think I paid about $50 for the Mercedes, which is pretty good value. The mesh wasn't great, but I fixed it up and it was pretty good. But I think that if you're a beginner, those kind of meshes might be quite difficult to work with, because they are very big. And as I said, if you with the naive implementation, you're looking at 15 minutes for a render or something, you're not going to be able to iterate over changes very quickly. So what I'd recommend is you get a tool like Blender. I don't know if you've heard of Blender. but it's an open source 3D graphics package. And it's really full featured. It's quite amazing that you can get that now, and it's completely open source and free, and does all these amazing things. But if you get a program like Blender, then you can make your own scenes. So what I did when I started out building the triangle intersection algorithms is I didn't start out with like a 70,000 poly model, which would just be insane. I just started out with a very simple cube. And if you imagine a cube, it's got 6 faces, and each of those faces is split into 2 triangles. So you've only got 12 triangles there to work with. And then it becomes easier to sort of debug and figure out what's going wrong when problems inevitably occur.
So do you recommend doing this with Swift? Is this the right language for what we're doing? Or is this kind of just a fun project and we should really be doing it with C++?
Yeah, I guess it depends what you're trying to do. I think if you want to learn Swift and at the same time learn about graphics, I think it would be a really worthwhile project to do in Swift. Or if you know Swift already and perhaps you don't know very much C++, then it would be it would be a great way to learn about graphics. And I'd also say that ray tracing is actually a really, really, really good way to learn about graphics, just because you can get right into it. You can do the hello world thing with like a couple of 100 lines of code maybe, and you don't have to, if you look at like an OpenGL tutorial or a Metal tutorial, you've got like all this boilerplate that you have to use. You have to, especially with OpenGL, you have to set up all these platform abstraction layers, where you have to use a library like GLFW or something. And if you're a newbie, it's sort of really quite cognitively taxing. It's a lot of stuff to get in before you can even draw something on the screen. Whereas with ray tracing, if you look at like Pete Shirley's books, you're the first book, you're pretty much drawing within 15 minutes, you've got these quite pretty colors on the screen, and you're much more directly connected to what's happening. So you can, if you set up a quick build process, you can make a change to the code, build, look at the picture you made, make another change, build, and just keep iterating like that. And once you get into that sort of flow, it becomes really easy and quite fun, because you're always getting this very direct visual feedback. So I think Swift is a great language to do that in. If you wanted to get more serious and do something like I was talking about with the having a high poly mesh, or trying to implement all of the optimizations, especially when you get into things like SSE intrinsics, which is using something called SIMD. I don't know if you know what SIMD is, but SIMD is where you work on several values at once, and the processor can actually do that. So you could say, instead of calculating one ray at once, you could calculate four rays at once, for instance, if the conditions are right. Doing that kind of thing, you can do it in Swift, but it's I think Swift is, it sort of becomes a bit, the overhead for doing that kind of stuff in Swift is it's almost more than C++ in a lot of ways. So unfortunately, I'd probably recommend you just go the C++ route if you want to get serious. But yeah, maybe Swift, they'll fix that up in the future.
Okay, very cool. So we've got a little bit more time, and we wanted to get to another topic which you talked about how we're all developing wrong.
Yeah, that's one way of putting it. Yeah. I wouldn't so much say as we're all developing wrong. I think it's more
how about this? In your own words, modern programming languages often attempt to solve problems that don't exist. Much more.
Yes. I think that's probably more accurate. And I don't think there's this sort of any insidious kind of no, we're doing it, we know the right way, and we want to do it this way anyway. I think it's sort of something that's crept in to modern languages and modern ways of doing things without actually really being, anyone being aware of it. It's sort of just crept in, and now all of a sudden it seems to be everywhere. And the idea is that a lot of modern languages, they operate on, or they're built on this philosophy that the programmer doesn't know what they're doing, and they try and save the programmer from themselves. And in the process, they actually hide a lot of the things that you really need to know to do, to make something good or make something optimized and fast, for instance. And while, in the short term that might help you, and I don't disagree that, having high level abstracted languages where you can very quickly do things is good. I think you also need to have that access to the low level, and you need to really have that underlying knowledge to be able to write fast and interesting programs. So to give you an example, if you look at something like Swift, and don't get me wrong, I do like Swift. I do like some parts of Swift. But if you look at something like Swift, like pointer manipulation in Swift, it's harder than C++. It takes more, it's like more cognitive overhead to do some pointer manipulation in Swift. And at that point, I'm sort of questioning, well, what problem are we actually solving with Swift? Because it's not Swifter, if you know what I mean. So that's one thing.
Developers are people just like us, and a lot of times they have really, really interesting stories about how they got into a programming language, out of a programming language, how they got into programming in the first place. I can't tell you how many people I've talked to that have a degree in music or have some affinity for music, or maybe they have a degree in something else like theater, and then they wound up getting into programming for other reasons. I actually used to work with a whole team of people that all had law degrees that wrote code. It's just interesting to me how people have come along in their careers as developers. So we have a show for you. So if you're into Ruby, go check out My Ruby Story. That's at myrubystory.com.
And then another thing is, like, I think another problem that we're severely neglecting as an industry is how to focus on things that encourage more productivity. So I'll give you an example. If you look at build times in Swift are very, very, very slow. Even the ray tracer I worked on, the exact same code in C++, I think it was 500 milliseconds to compile. Swift was about 5 or 6 seconds. So that's a huge difference. And if you multiply that out, it becomes even worse. And it just means that your whole workflow is slower. So every time you want to make a change, you have to wait longer. That means you make less changes. That means you can make less improvements because you can't see all of the options. And it sort of just has this quite cumulative effect where it seems like a small thing, like having a longer build time. Or, who cares really? I'll just go get a coffee or whatever. But it actually has a huge impact on your productivity as a programmer. So I'd really like to see modern languages focus on that. How can we make you more? What kind of features can we add to make it more productive for you, rather than here's the flavor, here's the new API flavor of the month, or whatever. While that stuff's cool, like it doesn't really matter if it takes like a minute just to see what changes, what the results of your changes.
When it comes to iOS or Swift specifically, sorry. Do you think that these are improvements that should be made in the tooling side in Xcode or in the language itself?
Yeah, they're probably both, I think. Like, I'd love to go to a WWDC and just say, hey, we didn't make any new APIs this year, but we sped up the build times by, 4 times or something. Because that would make a huge difference. That would just make a huge difference to being able to, iterate over ideas. Because if you're a programmer and if you're designing like a UI or something, or like a sort of a quite complex algorithm, then you want to be able to see the results of that, and you want to be able to see it quickly. So I think it's probably a bit of both. Like, it's probably down to the way that Swift is built, for instance. Maybe there are a lot of type checking, and there's a whole bunch of stuff in there in the compiler that probably slows things down a bit. But also the tools as well. Like, the tools are, I'll be completely honest, I don't even really use Xcode, even for iOS development. I'll actually use Vim, and then I'll just use Xcode as a debugger, because Vim's just faster. It's faster. It's quicker to move around files. It's quicker to make changes. I don't have to wait 3 seconds for the autocomplete to work. The autocomplete is just instant. And that's, those are little things that, once again, they add up a lot. And if you're doing an autocomplete, 300 times a day, then, 300 times 3 seconds is actually a lot of time. So So those kind of things I think are really important, and I really wish that Apple, and well, it's not just Apple, but everyone would focus in that direction much more.
Right. Well, I think the safety of Swift is part of what slows it down, because I know that I saw a talk at the Swift by Northwest last October, and I can't remember what the company was, but they were talking about what they had done to try to speed up their Swift project. Right. And one of the things that they found was that by not relying on type inference and instead specifying the type for all of their properties and variables, actually sped things up noticeable. It was enough of an improvement that they implemented it project-wide. Okay,
that's good to know. Yeah, so maybe if there are things the program can do there, then that's probably good as well. There's a really interesting talk, and a lot of the stuff I'm sort of just parroting what Jonathan Blow, Casey Muratori, the two programmers I look up to a lot, and they have I think I put a link in my document, but maybe we can share the link later. They did these really good talks about how software is getting more and more complex, and there must be some reasonable upper limit to that complexity. You can't just keep adding more complexity on top of complexity. And they sort of treating it almost to the point where it's becoming a bit of a crisis, and they want to I think a lot of the motivation for them giving these talks is to try and get people to reduce that complexity and let's try and make things simpler, because a lot of the problems we're solving aren't actually that hard, but we're making them very hard for ourselves just by having that extra complexity.
Well, cool. Well, thanks for sharing. I think we're all going to switch to C++ now, right? So.
Yeah, I wouldn't recommend C++ either. C++ has a whole bunch of different problems.
I was a professional developer for C++ for many years, and we had many compile time issues.
Right.
Hopefully Swift can catch up, and it makes me sad that people are making code changes to try and fix compile times, and what the right. They're not alone. A lot of companies are doing that, because if you have a large app, you've got 30-second compile times, which is rough.
Yeah,
that's a big drag.
Yeah. If you're changing the color of a button and you have to wait 30 seconds, then it's just your day's going to be very long.
Yeah, the new modern build system does speed things up enough that it was worthwhile to have it put in, but I think there's still a lot of improvements that can be made.
Right. Yeah. Yeah. Just going back to the C++ thing, even that's pretty slow. If you define all your C++ modules as separate objects that then get linked at the end, that's actually quite slow as well. But you can do things with C++, like you can do what's called the Unity build, where you just literally include all of your source files into one big source file, and it just compiles the whole thing, and it's super fast. It's really fast. I'd love to see those kind of speeds in Swift.
No, definitely. We're running a little bit short on time. Anything else we should cover before we get to the picks? Anything else you want to say?
Not really, other than just if you're a programmer and you're out there, I think it's really worthwhile. I think one thing I iterated on the TrySwift talk, and I think it's really worthwhile, is for people to really just get into things. Like if you want to learn about something, really get into it. Figure out how it actually works, and maybe go and build your own framework or build your own version of it, even if it's not anything that's going to be used commercially or anything that you want to release, but just for your own learning purposes, really getting into it. It's always worth it, I found. And I definitely found it with the ray tracing, just really getting into it, figuring out how the math worked, figuring out how the whole thing worked. It made a huge difference, I think.
Yeah, I think that's great advice. I remember when I was trying to understand MVVM, we were even using it in a project, but we were using a reactive framework to do it. And that kind of abstracted my ability to understand what was happening away. And I ended up following kind of a guide or a suggestion by Ian Keane on Slack who had made his own little framework for piping values back and forth. And so I just made my own also. And as soon as I did that, I just understand the whole concept completely. Right, okay. It wasn't magic anymore.
Yeah, there's some famous quote where you say if you can only truly understand something if you build it yourself, or something like that. That sounds I think that's absolutely true. Another example is I'm doing some OpenGL stuff now, and it's all just so much easier now that I've done the ray tracing stuff, because a lot of that knowledge sort of carries on quite nicely.
Very cool. Well, let's get to the picks. Abby, what do you have for us?
Sure. I actually have an app that I discovered yesterday. It's called Aumi. I hope I'm pronouncing that right. It's AUMI. And it's an app that was built by an 18-year-old named Ethan Shellcross. And it's a daily activity and mood tracker. Basically, it's for like healthy mental self-care. And he built it because he's autistic or on the autism spectrum. And he wanted to build it for people like him to manage his symptoms and their symptoms, because he couldn't find anything that, that really fit his needs. And the app is so well done. I'm completely floored that this is his first release and that he's only 18. It's really well done. It's nice looking. It's only on its like 1.2 release right now. There's some UI issues a little bit, but he interacts with people on Twitter and he's getting those worked out. And I really think that it'd be really helpful for people who have anxiety or ADHD or any other kind of like mental health challenges, because there's this, it prompts you, how you could say every half hour, every 2 hours, whatever you want, it prompts you to record your mood. And instead of doing a calendar type thing for your daily activities, it uses an energy level thing. So, you start the day, you say how much energy you have on a scale of -10 to +10. If I wake up in the morning and I feel drained, I might say I've only got 3. And then you list the activities you're doing each day with an energy rating that could be negative or positive, because maybe relaxing is positive energy, but going grocery shopping is a drain. And so it allows people to see where they're sitting for their energy levels, and if they've planned too much for that day, if it's going to take too much out of them, if they need to put in some more rest time. I'm just really, really amazed at what a great job he did with this. So again, it's AUMI.
AUMI, it's just about us. It sounds cool.
Awesome. Yeah. Put a link in the show notes to that and we'll
sure.
So we can check it out.
I was going to say, I think there'll be a lot of, in the future, there'll be a lot of room for those kind of apps, ones that help you sort yourself out, if you know what I mean, like almost like self-help apps or something, really, helping you sort out your mental state and your
I think his main goal was that there's a lot of apps out there that kind of do try to do mood tracking, or they give you meditations, or they do all kinds of things, but they're not made by people who are autistic, and so nothing fit his needs. Like there's even a part inside it with a sensory profile, so you can rate, if which I think would be great for parents to put in their child's sensory profile. So if you're very sensitive to light but not sensitive to sound, and very sensitive to touch, and also can say like how to tell if I'm upset. So if a caregiver or a stranger is handed the phone by a kid who's like having a meltdown, they can look and be like, okay, I can't touch this kid, but if I talk to them, it'll calm them down, because all that info is in there.
Okay, yeah.
No, it's very cool. I look forward to checking that out. It's an important issue. Capsy, do you have a pick for us?
Pick? Well, I'll have to. It's going to be. Can I give a YouTube talk? Is that okay?
That's all good.
Okay, great. So a YouTube talk. It's by a programmer I respect and admire. It's called The 30 Million Line Problem. And it's a very interesting talk. It's probably a little bit controversial. Like, not many people, it'll probably divide a few people, but it really makes you think. So I don't want to explain it too much, but it goes into the idea that sort of touches on what I was talking about before, where if you do a very simple operation, say in your web browser, you're actually touching millions and millions and millions of lines of code. Like if you look at the entire code base of every single API and every single piece of software and all of the hardware and all of that stuff in between, you're touching a unimaginable amount of code. And he sort of goes on to explain that this isn't actually necessary, and we can actually do much better here. We can make things much faster and much more stable, much more secure even, with some more thoughtful kind of hardware design. And he goes on to talk about something called a common ISA, which I can't really explain too much here, but it's a very interesting talk. It's quite thought-provoking.
Awesome. No, I look forward to checking that out. So Capsy, if people want to find you, how can they find you?
Twitter's the best place. I'm Capsy1312. Send me a message. Love to hear from you.
Okay. Well, great. Well, thanks for coming on the show. I learned a lot about ray tracing, and I got some more ideas for how we can improve programming languages and compilers. For everyone else, we'll talk to you next week.
Great. Thanks for having me, Jaim.
Sure.
Yeah, have a great day. Bye.
You too. See you later.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit